Hey everyone, we're on chapter 10 now, going over systems of equations and inequalities. These next videos are going to go over chapter 10.1 to 10.2. So in this video, we're going to be going over 10.1, which is systems of linear equations in two variables. So a system of equations is a set of equations that involve the same variables. So we're going to have multiple equations and the variables are going to relate to each other. A system of linear equations is a system of equations in which each equation is linear, hence the name linear equations. The solution of a system is an assignment of values for the variables that make each equation in the system true. So in this case, we're going to be solving for a solution, and it has to satisfy not only one equation, but all the equations in the system. So it can't just satisfy one. So to solve a system means to find all solutions of the system. So for example, if we have 2x minus y equals 5, that's our equation 1. And then we have x plus 4y equals 7, which is our second equation. And say we knew our solution, a possible solution was 3, 1. So by plugging that in to equation 1 and equation 2, we have that it satisfies both. So when you plug in 3 for the x, you get, and 1 for the y, you get the equality correct, and it satisfies both equations, so that is indeed a solution to the system. So graphically, coordinates of a point of intersection give the system solution. So if we were to graph 2x minus y equals 5 and x plus 4y equals 7, the point 3,1 lies on both lines and is the intersection, so it's a solution. So let's go ahead and look at the different methods that we use to solve these systems of equations. So our first method is the substitution method. So we start with one equation in the system and we solve for one variable in terms of another. So our first step is to solve for a variable. So you choose an equation and you solve for one variable in terms of the other. So say you solved for x and you're doing it in terms of y. And then we substitute. So we substitute the expression that we found in step 1 into the other equation to get an equation in one variable. And then we solve for that variable. And then we back substitute. So whatever value we found in step 2, we're going to substitute that back into the expression found in step 1 to find the remaining value. So let's go ahead and do an example of this to see how that plays out. So for example, we have 5x minus 4y equals 9. And then I have x minus 2y equals negative 3. So those are our two equations. So I'm going to go ahead and use equation 2 and solve for x. So I'm going to do step 1. So I solve for x in terms of y, and I get x equals 2y minus 3. And then our second step is to substitute this expression into the other equation to get an equation in one variable and then solve for that variable. So I'm going to use the first equation, 5x minus 4y equals 9, and then I'm going to substitute the x I found in step 1 for the x in that equation. So I'm going to get 5x, and then our x is 2y minus 3, minus 4y equals 9. And then I solve for y, because now my equation's in y. So I have 10y minus 15 minus 4y equals 9. And then I get y equals 4. And now I'm going to back substitute. So I could substitute my y equals 4 into equation 1 or equation 2, which is this first thing that I did. I substituted it into equation 1. Or I could substitute it into this equation, but I solved for my x here, so I could use this one. Usually this one is better to do, which is this bullet, because our x is by itself already, but really you could use either equation to solve for the remaining variable. So I did it both ways, but you could choose which way you want to do it, and then I get x equals 5. So you normally take a moment to check that your solution satisfies both equations. So if you take a moment to check, that our solution 5, 4 satisfies both equations, and it does. And so our solution set is 5, 4. So our next method is the elimination method. So we try to combine equations using sums or differences so as to eliminate one of the variables. So for our steps, we have our first step is to adjust the coefficients. So you multiply by one or more of the equations by appropriate numbers so that the coefficient of one variable in one equation is the negative of its coefficient in the other equation. So the key here is that we want to get basically opposite values of a variable, and so when we add them, they're going to cancel, and then you eliminate that variable basically. So you're going to add the two equations to eliminate one variable, then solve for the remaining variable. So really we could subtract as well. So the key is that you have opposite signs. So if you are subtracting the two values, that's basically multiplying by a negative as well. But usually you want to get them where it's a positive and negative, and then you're adding the equations, just makes it easier. And then we back substitute. So we substitute the value that we found in step 2 back into one of the original equations, and we solve for the remaining variable. So let's do an example to see that play out. So I have 3x plus 2y equals 14, and then I have x minus 2y equals 2. So I have both of them, and I don't need to I don't need to multiply the equations by any sort of constant because I have 2y and negative 2y. So I already have a variable with coefficients that are opposites of each other. So now I could add and move on to step 2. So when I add the equations, I get 4x, and then my y's cancel, equals 16. So my x is 4. And then I could go ahead and plug in x equals 4 into equation 1 or equation 2. So I just go ahead and use equation 2, and I get y equals 1. So my solution set is 4, 1, and you could check that the solution satisfies the system. So my next example, I have 2x equals 7y minus 17. Then I have 5y equals 17 minus 3x. So I go ahead and write the equations in the form ax plus by equals c before solving, just so we have the correct variables on top of each other, and so the form is just nicer and easier to solve. And so we do that to set it up. So I just have 2x, I subtract 7y, so I get 2x minus 7y equals negative 17. And then I add 3x, so I get 3x plus 5y equals 17. And we have the correct variables on top of each other. So I go ahead and I want to cancel the x's here. So I go ahead and figure out what's the least common multiple of 2 and 3, and that's 6. So I go ahead and multiply the top by 3, and then I'm going to multiply the bottom, equation 2, by negative 2, so I get opposite signs of 4, 6. So in the equation 1, I get 6x minus 21y equals negative 51. And equation 2, I get negative 6x minus 10y equals negative 34. And then I add these equations, and I get negative 31y equals negative 85. So then my y is 85 over 31. So I could back substitute this in, this y equals 85 over 31 into either of my equations. But I'm going to go ahead and just start from the beginning and instead solve for my x and eliminate y to solve instead of substituting the fraction back, just because it's a complicated fraction. I don't want to have to deal with that. So I'm going to do it this way. So I'm going to try to eliminate y now. So the least common multiple of 7 and 5 is 35. And I could just multiply them by positive coefficients because I have a negative 7y and a 5y. So one of them's already going to be negative. So I multiply the equation 1 by 5 and equation 2 by 7. And I get 10x minus 35y equals negative 85. And then I get 21x plus 35y equals 119. The y's cancel, and I get 31x equals 34. So my x is 34 over 31. So my solution set is 34 over 31, 85 over 31. So my last method of solving systems is a graphical method. So we go ahead and use a graphing device, such as a graphing calculator or Desmos.com to solve. So our first step is to graph each equation. So we express each equation in a form suitable for the graphing calculator by solving for y as a function of x. And then we graph the equations on the same screen. So we want to find the intersection points because the solutions are the x and y coordinates of the points of intersection. So for example, I have find solutions of the system. I have 1.35x minus 2.13y equals negative 2.36. And then I have 2.16x plus 0.32y equals 1.06. So I solve for y in terms of x so I could graph. So I have y equals 0.63x plus 1.11. And I have y equals negative 6.75x plus 3.31. Now I'm going to go ahead and use a graphing calculator or Desmos.com, and I find that my solution is 0.3 and 1.3. So I'm going to go ahead and do that now. Okay, so we're going to go ahead and graph our system of equations here on Desmos. So I have y equals 0.63x plus 1.11, and then I have y equals negative 6.75 x plus 3.31. Okay, so let's look at the intersection point. That's going to be our solution. So we have our solution is, it's about rounded, it's about 0.3, 1.3. So that's our solution to the system. Okay, so the number of solutions of a linear system in two variables is given by one of the three options. So our number solutions, if we have exactly one ordered pair solutions, graphically this means that the two lines intersect at one point. If we have no solution, then the two lines are parallel, and then if we have infinitely many solutions, the two lines are identical. So here on the bottom we have the graphs. As you can see, we have exactly one solution, the two lines just intersect at one point. If we have no solution, we have a pair of parallel lines, so they're never going to touch, never going to intersect, so we have no solution. And if we have infinitely many solutions, that means that the lines are actually on top of each other. So they intersect basically at every point, so we have infinitely many solutions. So a system with no solution is said to be inconsistent. A system with infinitely many solutions is called dependent. Okay, so in this example, I have 4x plus 6y equals 12, 6x plus 9y equals 12. So I'm going to go ahead and multiply by 3 and multiply by negative 2 because I have the goal of canceling out the x's. And the least common multiple of 4 and 6 is 12. So if I do that, I have 12x plus 18y equals 36. Negative 12x minus 18y equals negative 24. So my x's and y's actually cancel, and I get 0 equals 12, which is not true. So 0 does not equal 12. So this means that essentially there's no values for x and y, which 0x plus 0y equals 12. So we don't have an x and y that satisfy this. So our solution set is the empty set. So that's what this means, the empty set. So our solution set isn't 0, it's the empty set. And so our system is inconsistent. So our next example, I have y equals 3x minus 2, and 15x minus 15y equals 10. So I'm going to go ahead and use substitution method because I already have my y by itself. So I could do 15x minus 5 of 3x minus 2 equals 10. I distribute and my 15x's cancel and I get 10 equals 10. So this statement is true for all values of x and y. So whatever value I choose, it's always going to equal because 10 equals 10. So we write this solution as x and y such that y equals 3x minus 2, which is our equation that we have here. So we could choose basically any x and any y such that this is true. And then I have x or x and y such that 15x minus 5y, 15y equals 10. So whichever x and y's, if this is satisfied, then that's our solution set. So basically these two lines coincide with each other. So they're the same line, so either one works. Okay. Now modeling with linear systems. So these are some guidelines to model with our system of equations. So our first step is to identify the variables. So we're going to identify the quantities that the problem asks you to find. And usually you need to read super careful. And then we introduce notation for variables. And so we usually call these variables x or y or just whatever letter you want. And then you express all unknown quantities in terms of the variable. So we want to express those, the unknown quantities in terms of the variables we define in step 1. And then we set up a system. So we want to find facts that basically relate the relationships between the expressions and variables we found in the previous steps. And then we set up a system of equations. And then we solve the system and interpret the results. So for example, I have a woman rows a boat upstream from one point on a river to another point 4 miles away in 1.5 hours. The return trip, traveling with the current, takes only 45 minutes. How fast does she row relative to the water, and at what speed is the current flowing? Okay, so we want to find the rowing speed and the current speed. That's here. Row relative to the water, how fast, and then speed of the current. So I'm going to let x equals rowing speed and y equals current speed. And here's the picture. So I have my dock from one point of the river to the other. And it's 4 miles away. Alright, so I'm letting my rowing speed be x, current speed be y. Alright, so I have two speeds. I have the speed that it took to go upstream. So by going upstream, this is upstream. This is when I'm going upstream. So when I'm going upstream, I'm actually working against the current, because the current is flowing this way and then I'm going this way. So the current is the green arrow. So I'm going to subtract my rowing speed, going to subtract the current speed from my rowing speed because they're working against each other. And then my speed downstream, when I'm going downstream, I'm working with the current. So the current is helping me go faster, and I'm not working against it. So the speed is combined. So I have x plus y. Okay, so my speed upstream times my time upstream is my distance that I travel. And that's trying to relate all these values together because I'm given time, speed, and distance. So my speed upstream times my time down upstream is the distance traveled. My speed downstream times the time downstream is the distance traveled. And I want to find my speed. Okay, so I can plug in my values. So I have my speed upstream is x minus y. My time upstream, so rowing the boat 4 miles away took 1.5 hours. So 1.5 hours in minutes is 90. And then relative to an hour, 60 minutes, so 90 over 60 hours is 3/2 equals the distance traveled. Distance traveled is 4 miles. And then my next equation is my speed downstream, which is x plus y, times it took me 45 minutes to travel downstream. So I have x plus y times 45 over 60 hours. And I have that's 3/4 equals the distance traveled is still 4 miles. So these are my two equations for my system. So I just multiply the first one by 2, and then I distribute just to cancel out the fraction. So I get 3x minus 3y equals 8. I multiply the second one by 4 to cancel the fraction, and then I distribute, and I get 3x plus 3y equals 16. Okay, so now I'm going to go ahead and multiply the first equation by 2. So I get, let's write it out. I get 6x minus 6y equals 16. And then I'm going to multiply the second equation by 4. So I get 12x minus 12y equals, let's see, 16 times 4, 64. Okay. And then by doing that, what am I doing? Sorry about that. So by multiplying by 2 and 4 and canceling the fractions, I already get opposites. So the y's cancel, and then I'm adding, so I get 6x equals 24. And then I divide by 6, and I get x equals 4. So I go ahead and plug that back in, our x equals 4 to get my y. So I get 3 times 4 minus 3y equals 8. So I get negative 3y equals 8 minus 12, which is y equals 4/3. So my x is 4 and my y is 4/3. So the woman rows 4 miles an hour because my x is my rowing speed. And then the current flows at 1 1/3 miles an hour because my y is 4/3. And that is the current speed. So those are my solutions. Okay. So my next example is involving mixtures. So a vintner fortifies wine that contains 10% alcohol by adding a 70% alcohol solution to it. The resulting mixture has an alcoholic strength of 16% and fills 1,000 1-liter bottles. How many liters L of the wine and of alcohol solution does the vintner use? So I have X is the amount of wine used. So it contains 70% alcohol, adding 70% alcohol solution to it. Result has strength of 16%, fills 100 1-liter bottles. So we want to find liters of wine and alcohol solution used. Okay, so my unknowns. So I have X equals the amount of wine used in liters. Y equals the amount of alcohol solution used. So the wine the resulting mixture, the wine contains 10% alcohol, and then the solution contains 70% alcohol. So that's our first, that's from this beginning part. Okay. So the amount of wine used is X. The amount of alcohol solution used is Y. The amount of alcohol in the wine is 0.10X because the wine contains 10% alcohol. The amount of alcohol in the solution is 0.7Y because of these values. Okay, so the volume of the mixture, the resulting mixture, must be the total of the two volumes the vintner is adding together. So I have the amount of wine used is X, and the amount of alcohol solution used is Y. So I have X plus Y, and it fills 1,000 1-liter bottles. So my total volume is 1,000. So the amount of alcohol in the mix must be the total of the alcohol contributed by the wine and alcohol solution. So that means that my 0.10X is the amount of alcohol in the wine, plus 0.7Y is the amount of alcohol in the solution, and that has to equal the resulting mixture has an alcoholic strength of 16%, so 0.16 times 1,000. So I get 0.1X plus 0.7Y equals 160. So I just multiply by 10 to get rid of my decimals, and I get X plus 7Y equals 1,600. So I have my two systems of equations. So I have X plus Y equals 1,000, and X plus 7Y equals 16,000. So I'm going to go ahead and I have my equation here, my system, and I'm just going to subtract equation 1 from equation 2. So this is equation 1, equation 2. So I'm going to subtract this one from equation 2. So it's essentially just multiplying equation 1 by a negative and then adding. So I get 6Y equals 600. Divide by 6, I get Y equals 100. And then I could plug that into my equation. So I have X plus 100 equals 1,000. So X equals 900. So the vintner uses 900 liters of wine and 100 liters of the alcohol solution. Okay, so that's it for this video. I'll continue the next video with chapter 10.2, Systems of Linear Equations and Several Variables. So just follow me there.